Hi, my name is Josh Gehring, and I'm a mechanical engineering student here at SDSU.
My name is Cole Brown, and I'm a mechanical engineering student here at SDSU.
My name is Joshua Bierschbach, and I'm a mechanical engineering student at SDSU.
I'm Ray Munsterman, a mechanical engineering student with SDSU. We are the HRST FBI team. We spent the year working with HRST, our sponsors, to develop this, a fabric bonding iron. HRST offers a penetration seal for the entry and exit of heat recovery steam generators. These seals look something like this, and they need to create a seam typically this long or even longer. To do so, they currently use an iron that's a little heavy and a little clunky and has a very short heating surface, not long enough to cover the whole seal at once. Installers of these seals are very frustrated with the process, so we sought to develop an iron that could minimize the time it takes to do this process and create a seal that's stronger than this one.
Some of the constraints defining this iron's capabilities were that the iron must reach a temperature of 550 degrees Fahrenheit to properly bond the fabric. It must have a heating plate dimensions of 18 inches by 4 inches and weigh less than 15 pounds while functioning under 110 volts and 15 amps for compatibility with common electrical outlets. The old iron costs $1,500, reaches 550 degrees Fahrenheit, weighs 13 pounds, and has a heating surface of 6 inches by 3 inches.
We started the design process by centering it around a metal plate on the bottom of the iron that was 18 by 4 inches, which met the first constraint set to us by HRST. Using this, we then modeled a few different irons in SolidWorks, and then throughout the process, we then came up with the final design that looks very close to the final produced iron. Throughout the design process, we came up with different materials that would both cut down on weight while keeping the iron strong and meeting the constraints. So over time, we had calcium silicate as our main insulator within the iron, but then we switched to pyrogel because it would both cut down on the weight substantially, it would reduce the cost, and it would do a better job of insulating the material.
The last couple things we had to focus on were the type of heating element and the way we were going to control that heating element. We considered a couple of different types of heat resistance wire layouts if we were to just run the heat resistance wire through the iron, through the metal plate that we use, but that would require quite a bit more work to install, and if there were any problems with it, then we couldn't really replace it easily. So we opted for a heater cartridge, which is the same thing, but it's all coiled up into a cylinder. It's easy to replace. To control it, we ended up going with a temperature controller, digital temperature controller, so that we could use different thermocouples if need be to get more accurate reading, and we could also set the hysteresis or the overshoot on the values, so it could accommodate for any overshoot on its own, and then we could also accommodate for any error with the thermocouple itself.
To manufacture the prototype, the base size of the heating plate was cut from a larger piece of aluminum, milled down to 3/4 of an inch, and a drill press was used to drill out a hole for the heating cartridges and a temperature probe. With an estimated $441, the iron that we designed can reach temperatures over 550 degrees Fahrenheit, weighs only 10 pounds, and is 18 inches by 4 inches. On top of these requirements, we also reached a stretch goal of making the irons hands-free with a hanging apparatus.
To conclude, our iron ended up meeting a lot of standards for HRST, and it helped them out in a number of different ways. The cost of iron is quite a bit cheaper, from around $2,000 for the existing iron. Our prototype, at least in production, would be around $500, and even a little bit less, maybe around $450. And so massive savings there. The effort that it actually takes to install these seals was completely removed. Nobody has to hold up a 13-pound iron for up to 45 minutes or an hour. They can just leave it be and it'll do its thing. It also saves a ton of time because it gets up to temperature a lot quicker, and it also seals off the entire seal at once rather than the smaller iron only getting certain portions of it at a time. The last thing is we have some quality assurance for the seals. There aren't going to be people kind of getting lazy or I guess impatient and inconsistent with where they place the iron on different parts of the seal. It should seal up entirely across the whole seal. I'd like to put out a massive thank you to everybody on our design review team that helped us through the project, as well as those of our sponsors that have really given us an opportunity to prove ourselves and to grow as students and potentially into work kind of carry a little bit more experience. So that includes our design review team at school, which was Dr. Doom, Dr. Mickna, Mr. Doug Peters, and Mr. Jason Sternhagen. They all helped us incredibly well with heat transfer, machining, electronics, and just general advisement, and it was very huge for us. And then, of course, Soren and Evan at HRST, they did a great job at giving us direction, kind of telling us what they wanted, and pointing out areas where we weren't quite meeting their expectations, or supporting us when we were very successful. So I appreciate that and wish I could say thank you in person. Last up is going to be our contact info. You can just go ahead and send us an email if you have any questions about what was contained in this video and how we kind of worked through a process, or if anything's unclear on what we did, please feel free to reach out. Thanks for watching. Thanks for taking the time.